In this video, we're going to talk about another way to multiply two vectors together, which is called the cross product. Now, the cross product is going to be different from the dot product in a number of extremely substantial ways, but it's going to have its own set of really interesting applications. Now, to give you the formula for the cross product, I, as the instructor, have a couple of different options for how to teach you that formula. However, I know that many of you are going to move on to take Math 240 within the next couple of quarters. And so I've decided that I want to teach you about something called a matrix determinant, because that is one really convenient way to define the cross product, but it's also going to be useful for you in Math 240 itself, for its own set of applications within that course. So beginning today, we're going to talk about the determinant of a 2x2 or a 3x3 matrix. It's going to be useful for us today, but it's also going to be extremely useful for those of you who are taking Math 240. If you have any intentions of taking linear algebra, don't forget this formula. Then we're going to use that determinant to define the formula for the cross product, and we're going to get some practice calculating that. Then we're going to talk about some properties of the cross product, and we're going to use them to find, first of all, to find a vector perpendicular to two given vectors, and second of all, to calculate a physics quantity known as torque. Alright, so to get started, I want to talk to you about matrices. And a matrix is just a table of stuff. A table filled up with potentially numbers, might have functions in it, might have vectors in it, or some combination thereof. Now in our class, we're going to be dealing mainly with tables with matrices that contain numbers and vectors. In linear algebra, you're going to be dealing with tables that have numbers in them. And if you intend to take differential equations, what we call here Math 238, in 238 you'll be dealing with matrices that are filled up with functions. But in general, it's just a table, like you would see in an Excel spreadsheet, a table with stuff in it. For a quick example, let's consider the table 2, -1, 3, 5. Now, notice the notation that I'm using here. The table is enclosed with square brackets. And then the four numbers in the table are arrayed within those square brackets. We generally don't write in vertical and horizontal lines to separate those numbers because it just gets cluttered. So we just arrange them in this form where we have 2 in the upper left corner, -1 below that, 3 in the upper right corner, and 5 below that. This would be an example of a 2x2 matrix. 2 rows, 2 columns. We could just as well give you a 3x3 matrix. A 3x3 matrix with 3 rows and 3 columns. And if I wanted, I could fill it all up with numbers, but I could just as easily put some vectors in there. For example, maybe I want to give you the matrix where the standard basis vectors i, j, and k are in row number 1. And the numbers 2, 0, and 4 are in row number 2. And 3, 1, and -7 are in row number 3. This would be another example of a matrix, which is 3x3, 3 rows, 3 columns, this time filled with a combination of vectors and numbers. Now in our class, we will be focused in particular on so-called square matrices. And a square matrix is just one where the number of rows is an exact match to the number of columns. For example, 2 rows and 2 columns, 3 rows, 3 columns. And if you have a matrix, which is square, then you can take that matrix and calculate an associated number called the matrix determinant. Now the formula for the determinant is different depending on the size of your matrix. If you have a 2 by 2 matrix, such as A, B, C, D, the determinant of that matrix is first of all denoted using absolute value bars around the matrix. Sometimes you may also see this written as A, B, C, D, where the square brackets have been removed and only the vertical absolute value symbols have been included. This is the notation for the determinant. The determinant formula is given by the number, which is found by taking diagonal products. Multiply the number A in the top left corner by its diagonally opposed number D. Then subtract what you get by going along the other diagonal, AD minus BC. For exercise, let's calculate the determinant of the following matrix. 2, 3, negative 4, 1. First of all, I would represent this in notation as vertical bar, the number 2, 3, negative 4, 1. This is the notation for the determinant of the matrix. And I can calculate this number by going along the primary diagonal, 2 times 1, taking that product, and then going along the anti-diagonal, subtracting 3 times negative 4. So sometimes you'll see me, as a mnemonic, write this little X symbol in between, 2 times 1, and then 3 times negative 4. So that number is equal to 2 plus 12, result 14, the determinant of this matrix. Now when you're looking at a 3 by 3 matrix, the formula becomes quite a bit more complicated. So the determinant, vertical bar, of the matrix, so let's say we have numbers A1, A2, A3 in the top, then B1, B2, B3 in the second row, and then C1, C2, C3 in the third row. This is how you would calculate this determinant. Okay. First, you look in the top left where A1 lives. A1. You're going to take the number A1 and you're going to multiply it by the determinant of a smaller matrix. You're going to multiply it by the determinant of what you get when you exclude the row and column containing A1. That leaves this guy in the lower right corner, B2, B3, C2, C3. Then you're going to alternate in sign. And you're going to go from plus to minus. And you're going to move over to A2. Take the number A2 and multiply it by the determinant of the matrix that you get when you eliminate the column and row containing A2. So, if I eliminate the column and row containing A2, all that's left is B1, C1 and B3, C3. And finally, move over to A3. A3 alternates sign again, so now it's back to being plus. Take A3 and multiply it by the determinant of the matrix that you get by excluding the row and column containing A3. So what's left is B1, B2, C1, C2. So moving along the top row, take A1, A2, A3 in turn with alternating signs plus minus plus, and multiply each of those by the determinant of the matrix excluding the column and row containing that A that you're working with. Okay, so let's try it with the following matrix. Now, yes, I will admit that this is kind of a huge pain to calculate, but this quantity is so useful for so many different things that it's really important to remember this formula. So let's go ahead and let's use it in the following example. Calculate the determinant of the following 3 by 3 matrix. So here I go, vertical bracket, top row, bottom row, third row. So the first thing that I'm going to do is I'm going to take the number in the top left, which is the number 1, and I'm going to multiply it by the determinant of the matrix that I get by excluding the first row and the first column. So that will be equal to -1, 0, -3, 4. So after that, alternating sign, I'm going to subtract what I get when I take the number in the second column, first row, and then the determinant of the matrix that I get by excluding that row and that column. And then alternating sign back again, I'm going to add plus the number in the third column, top row, 0, times the determinant of the matrix that I get by excluding that first row and that third column. 2 minus 1, 0 minus 3. So now, to calculate these quantities, I can use the formula for the 2 by 2 matrix determinant, which says take the product on the prime diagonal, subtract the product on the secondary diagonal. And let's calculate what we get from each of those. So the first quantity is 4 times -1, which is -4, minus 0 times -3, which is 0, times 1. Then subtract 2 times 4. 2 times 4 is 8. Subtract 0 times 0, result 0. That's times 1. And then the last determinant, we have 2 times -3, -6. Take away 0 times -1, result 0, times the number 0. Okay, so finally all the matrix determinants have been calculated, and all that's left is a little bit of arithmetic using PEMDAS. So for example, we have -4 minus 0 is -4, -4 times 1 is -4. We have minus 8 times 1. 8 times 1 is 8, so we're subtracting 8. And then we have -6 minus 0 is -6, times 0 is 0. So this 3 by 3 matrix determinant is equal in value to the number minus 12. Yes, this really is what it takes to calculate a 3 by 3 matrix determinant by hand. It's quite labor intensive. Let's practice finding the determinant of this matrix, and this is the kind of matrix that we will really need for our purposes today. The matrix with the vectors I, j, k in the first row. So, to calculate the determinant of this matrix, I, j, k, 1, 0, negative 1, 0, 2, 3. I'm going to take the first number in the first row, quote unquote number. I'm going to take the vector I, multiply it by the determinant of the 2 by 2 matrix that I get by excluding the first row and the first column. Alternate sign, so minus is next, minus. Now I'm going to take the second number in the first row, j. The vector j multiplied by the 2 by 2 matrix determinant, excluding the first row and the column containing j. Alternate sign again, so now we're back to plus. Plus the third entry in the first row, k, times the matrix determinant, excluding k. So 1, 0, 0, 2. All right, so now let's calculate each of these individual 2 by 2 matrix determinants. We have 0 times 3, take away 2 times minus 1. 0 times 3 is 0. 2 times minus 1 is minus 2. 0, take away minus 2, times the vector I. Subtract what we get by taking the first diagonal, subtracting the product on the second diagonal. 1 times 3 is 3. 0 times minus 1 is 0. And finally, the last 2 by 2 determinant, 1 times 2, take away 0 times 0, 2, take away 0. So this becomes positive 2 times I, negative 3 times j, and positive 2 times k, which works perfectly well as a final answer. If you like, you can convert this to angle bracket notation, and you can finish this problem by saying that in this case, the determinant of this matrix is equal to 2, negative 3, 2 in components. This last example is what we will be doing when we calculate the cross product of two vectors. The cross product is a way of multiplying together 3D vectors. I have one vector whose components are v1, v2, v3, a second vector whose components are w1, w2, and w3. If I want to take the cross product of v with w, then I can take the matrix determinant where the first row is the standard basis vectors I, j, k. The second row are the entries of the vector v. And the third row are the components of the vector w. Now, one of the major differences between the cross product and the dot product is that while the dot product produced a number for the answer every single time, the cross product, the result of that calculation, will always be a vector. In the same way that the result of this matrix determinant with I, j, k at the top row was a vector when all the calculations were said and done. The cross product produces a vector. The dot product produces a scalar. Another difference between these two is that the dot product could be done even for 2D vectors, but again, the cross product is defined only for 3D vectors. Let's do a quick example and calculate the cross product between 3, 0, 1 and -1, 1, 0. So here's the vector v and here's the vector w. So I'm going to arrange the following matrix. In the top row we have the standard basis vectors I, j, k. In the second row, we have the entries of the first vector v, and I'm calculating the determinant of that matrix. Now you've seen two examples so far of 3x3 determinants. So I want you to pause the video and try and calculate this 3x3 determinant on your own. Try it as an exercise, and then resume the video and check and see if you get the same answer that I do. Alright, you tried it? Alright, let's see how it goes. So, we take the vector I in the first row and first column, and multiply it by the vector that excludes the first row and the first column. Subtract j, who lives in the first row and second column, exclude the first row and the second column. Then add k, who lives in the first row, third column, exclude first row, third column. And then let's take some diagonal products. We've got 0 times 0, minus 1 times I. We've got 3 times 0, minus 1 times -1 times j. 3 times 1 minus 0 times k. So this is the vector -1, -1, 3. The result of the cross product of two 3-dimensional vectors is also a 3-dimensional vector. Now the question says, follow up, go ahead and calculate the dot product of the result with each of the original vectors that we used in our cross product calculation. So let's calculate the dot product of -1, 1, -1, 3 with 3, 0, 1. 3 times -1 is -3, then -1 times 0, then 3 times 1, result 0. And if I do the same thing with the other vector, the result of the cross product, dot with -1, 1, 0, -1 times 1 is +1, -1 times +1 is -1, then 3 times 0 is 0, so the result of that is also 0. We took two 3-dimensional vectors, calculated their cross product, and the result was a third 3-dimensional vector whose dot product with the two original vectors was 0. In other words, if I take two vectors v and w and I cross them and I get a third vector, the result will always be orthogonal to the two vectors that we started with. So in other words, if the vector v, say, points horizontally, and the vector w, say, points front to back, then the vector v cross w will point straight up, and it will form a right angle not only with the vector v, but also with the vector w. Now this can be used in the following way. Suppose we wanted to find a vector which was perpendicular to both -1, 1, 0 and 0, -1, 1. How can we accomplish something like that? That can be easily accomplished by just taking the cross product of the two vectors. So for example, suppose that I crossed the two vectors where the first vector I was given comes first in the cross product, and the second vector I was given comes second in the cross product. Then this is equal to the vector I times the 2 by 2 determinant, excluding the row and column containing I, minus the vector j times the 2 by 2 determinant, excluding the row and column containing j, plus the vector I, 2 by 2 determinant of the matrix excluding the first row and third column, since that contains k. Now one by one, I go through and calculate these diagonal products. 1 times 1, take away -1 times 0. That scales the vector I. -1 times 1 minus 0 times 0, scaling the vector j. And then -1 times -1, take away 0, scaling the vector k, which is equal to 1 in the first component, 1 in the second component, and 1 in the third component. The vector 1, 1, 1 is perpendicular to the vector, both the vectors -1, 1, 0 and 0, -1, 1. You can confirm that by taking the dot product. Now, as you can tell, calculating the cross product is kind of a pain. It requires this huge arithmetic calculation involving all these sums and products, and it can be useful sometimes to be aware of some properties of the cross product, because that gives you a way to potentially save some time. One of the properties of the cross product is that if you scale one of the vectors, if you scale the first vector or if you scale the second vector, then that's the same thing as if you just scaled the result by that number. If v and w are parallel vectors and one is a scalar multiple of the other, then automatically the cross product between the two vectors is equal to the 0 vector. It's going to work out to be 0 in every single component. Now the third property of a cross product, which also is a bit of a warning, is that order in the cross product really does matter. It's not like products of numbers, it's not like dot products of vectors, where you can basically take the product in any order you want. If you take the product with v in the lead, with the entries of v in the second row, and the entries of w in the third row, you're generally not going to get the same thing as if you took the product with w in the lead and swapped the order, where w is in the second row and v is in the third. As a matter of fact, if you swap the order of the two vectors in the cross product, the two results will be exact opposites of one another. So if one of them is positive, has positive components, the other one will have negative components. Now, a few pages back, we calculated the cross product of 3, 0, 1 with -1, 1, 0, and we found that the result was equal to the vector -1, 1, 3. So someone says, using that information, can we recycle some of that information and calculate the cross product of -1, 2, 0 with 12, 0, 4 without having to do any more of this pesky stuff with matrix determinants? Now the thing that I'm going to use is that, okay, first of all, -2, -2, 0 is just a scaling by a factor of 2 of -1, 1, 0. And likewise, 12, 0, 4 is just a scaling by a factor of 4 of the vector 3, 0, 1. So properties number 1 and 2 tell me that I can basically factor those scalars out. I can factor those scalars out as 2 times 4 times the result of the cross product of the unscaled vectors. Now notice that the order here is the opposite of the order that we used when we did our calculation. So I can flip the order of those two vectors back to what it was before, but whenever I flip the order of the vectors, a minus sign appears. So, what have we learned? We've learned that the cross product of -2, 2, 0 with 12, 0, 4 is equal to a scaled version, scaled by -8, of the vector that we calculated in the previous exercise, -1, -1, +3. So without doing any shenanigans with matrix determinants, without any of that work, just recycling some of our previous calculations and using these properties, we can find that the cross product between these two vectors is +8, +8, -24, scaled by 2 and 4, and multiplied by a negative because the order of the vectors was swapped. Let's calculate the cross product of 3, -6, 12 with -2, 4, -8. Now, neither one of these vectors is related in any way to either the vectors that we had in our previous calculation, because these vectors had zeros as part of their entries, but these vectors have non-zero entries. However, what I am noticing is that these vectors appear to be scalar multiples of each other. If I took the vector 3, -6, 12, and I divided all the entries by 3, and I multiplied all the entries by 2, and I made the result negative, which means that the vectors are parallel, which means that their cross product is equal to the 0 vector. 0 in the first component, 0 in the y component, 0 in the z component, the 0 vector. So we got that for free without doing any calculations at all. Two parallel vectors crossed will always result in zeros in every single entry. Just like the dot product had a relationship to the angle between the two vectors, the cross product is also related to the angle between the two vectors, which I'm still going to go ahead and call theta. If you look at V cross W, and you take the magnitude of that vector, the number that is equal to the magnitude of V cross W is exactly equal to the magnitude of the first vector times the magnitude of the second vector times sine of the angle between them. Now, a few things of note about this equation. First of all, never use this formula. I can't think of a single situation where I would ever use this formula. To calculate the angle between the two vectors, think about how much work would be involved in doing such a thing. You would have to find the length of the vector v and the length of the vector w. You would have to go through this entire matrix determinant stuff to find v cross w. Then you would have to find its magnitude. You'd have to divide and then take inverse sine to calculate theta. Don't do it. Please don't do it. If you want to find the angle between two vectors, just use that dot product formula from the previous day. It's going to be so much faster. This formula is going to give us an explanation for a couple of different things. First of all, this formula is the reason why we have this property of the cross product, that if v and w are parallel, if they're parallel, then they either point in the same direction, in which case theta is equal to 0, or they point in opposite directions, in which case theta is equal to 180 degrees. In either case, though, sine of the angle is equal to 0, which cancels out the two magnitudes on the right side and forces the magnitude of the cross product to be 0. But the only vector with a 0 length is the 0 vector itself. 0 in every component. So this theorem provides an explanation for that property. And it will also provide an explanation for the formula that we are about to give for the physics quantity known as torque. To give you an informal definition of torque, the setting is this. We have some object in three-dimensional space which is being rotated around a central point. So someone comes in and they apply a force to this object. Let's say this is a door handle, for example, which is attached to the door at the point of rotation, and we come in and we exert a force on the door handle with our hand. Maybe the force that we exert on this door handle is given by this green vector F. Now, when we do such a thing, that force causes the object to rotate around the point of rotation. The door handle will be rotated, and that is what allows the door to open up. So the torque is the measure of the tendency of a force to cause an object to rotate. The torque is going to be dependent on a couple of different things. First of all, it's going to be dependent on how much strength is in the force that's applied to the object. If you just tap that door handle lightly with the tip of your finger, not much rotation is going to occur. But if you slam your entire hand down on that door handle with a lot of force, then the door handle is going to turn a lot and quite quickly. Torque is also affected by where you apply the force. If you apply the force very close to the point of rotation, then from experience we know it's going to take a lot more effort to rotate the door handle if we apply the force up here closer to the point of rotation. If we want to move the door handle easily, then we want to apply the force further away from the point of rotation and we place our hand closer to the end of the door handle. Torque is also affected by the direction in which the force is applied. If you applied a force which was parallel to the door handle and you poked it along its end, that's really not going to have any effect at all to rotate the handle of the door. If we want to rotate the door handle, the most efficient way to do that is to apply a force which is directly perpendicular to the handle, and that will cause it to rotate most efficiently. So the magnitude/strength of the force is affected by the length of this vector between the point of rotation and the point at which the force is applied. The magnitude of the torque is also affected by the strength of the force itself. And the magnitude of the force is affected by the angle between the thing that we are rotating and the force that's applied. So which formula just so happens to contain all of those different pieces? It's the formula given above. And this turns out to be the formula for the calculation of the magnitude of torque. How much of your force vector is causing a rotation in the object? The magnitude of torque can be calculated simply by taking the magnitude of the cross product between the force vector F and the vector V, which represents the object that's being rotated. As in the drawing above, the vector V stretches from the point of rotation to the point where the force is being applied. We can also see it in the following theorem, which has everything typed up in neat and an official, taken from a calculus textbook, an official picture of this situation in the case of having a wrench and the point of rotation is some screw or bolt that you are screwing into place. We have a force vector represented by the vector F, which is being applied to the end of a rotating lever, which is represented by a vector R, whose tail is at the point of rotation. Then the magnitude of the torque, using this notation, is the magnitude of the cross product between the vector representing the spinning object and the vector representing the force. So, as an exercise, let's consider a force represented by the vector 0, 3, 4. Negative 4. That's being applied to the end of a 0.25 meter wrench, which lies along the positive y-axis and grips a bolt at the origin. So the origin is where the bolt is located, that's the point of rotation. And then we have a wrench which is stretching 0.25 meters along the positive y-axis. So we could represent such an object by a vector that is pointing purely in the y direction, which has this quantity 0.25 units. That's how far we should go in the y direction. So what is the magnitude of the associated torque? This can be found by taking the cross product of F with R and then taking the magnitude of that vector. Once again, I encourage you to pause the video and try and calculate this quantity on your own as practice for when you're going to have to do it in the exercises. So that vector is simply -1 in the x component, and everything else is 0. So the magnitude of this is super simple. The magnitude of this is equal to the square root of -1 squared plus 0 squared plus 0 squared is equal to 1 unit. Whatever units are appropriate based on the units that would be given for the force vector. I haven't worried about that here. That concludes today's material. You're really going to want to get good at calculating determinants and cross products, because you're not going to just need it in this class. You're going to need it again in Calculus 4, you're going to need it again in Math 240, and you're going to need it again in differential equations. So the better you can get at calculating determinants, the more prepared you will be for those courses. To sum up what we did today, we gave the formula for the 2x2 and 3x3 matrix determinants, and then defined the cross product as a specific case of a matrix determinant, where the top row was ijk, the second row was the entries of the first vector, and the third row was the entries of the second vector. Then we looked at some properties of the cross product as they could be used to simplify or bypass some direct calculations. Then we looked at an application of the cross product to finding a vector which was orthogonal to two given vectors, and then we used the cross product to calculate the magnitude of torque.